10. That is how many M-class solar flares the sun fired in a single 24-hour window this week. After an X-class blast, the sun's most powerful category opened the barrage. The first hit knocked out radio signals across a stretch of the Pacific. Then the eruptions kept coming, hours apart, sometimes minutes apart, from the same patch of the sun. Several of them hurled clouds of charged plasma toward Earth. Right now, those clouds are stacked up and inbound, due to start arriving within hours. But here is the strange part. The day before it began, forecasters put the odds of an X-class flare at roughly 10%. The sun ignored the forecast, and the scientists watching it say their models cannot keep up with what it is launching. By the end of this video, you will know what this barrage actually means, and where the real danger lies. At 50 minutes past 8 in the evening, Universal Time, on the last day of June, a patch of the sun designated Active Region 4479 tore open. The eruption registered as an X1.1, X being the most powerful class of solar flare there is. In the same instant, on the sunlit side of Earth, high-frequency radio signals across a stretch of the Pacific northeast of Hawaii degraded and dropped out. Forecasters logged it as R3, a strong radio blackout, the third highest level on the scale they use. On a normal week, that flare alone would have been the story. This week, it was the opening shot. Over the following 24 hours, the sun fired 10 more flares in the M-class, the second most powerful category. A solar flare is a sudden release of magnetic energy from the sun's atmosphere, and scientists rank them on a ladder that runs A, B, C, M, X, each letter 10 times stronger than the one before it. Most days, even in an active year, the sun manages a scatter of minor flares and perhaps 1 or 2 M-class events. 10 in a single day is a barrage. The pace inside that window is the part worth sitting with. On the morning of July 1st, Region 4479 fired 4 M-class flares in under 2 hours, at 6:27 Universal Time, at 6:43, at 7:35, and again at 8:17. 16 minutes separated the first two. One of the field's best-known solar physicists reached for a blunt description, a machine gun sun. And every one of those blasts had finished its work before anyone on Earth could have reacted, because the damage traveled at the speed of light. To understand what those flares did, start with how the strike arrives. A flare's X-rays cross space at the speed of light and hit the sunlit side of Earth the instant our satellites see the flash. That radiation charges the lower atmosphere, and high-frequency radio, the long-range band used by pilots over oceans, mariners, and emergency services, degrades or drops out. Forecasters grade these radio blackouts on a scale from R1, minor, to R5, extreme. Now watch the footprints. Around midday on June 30th, an M5.9 flare put a moderate R2 blackout over the Atlantic west of Africa. That evening, the X1.1 blacked out a stretch of the Pacific northeast of Hawaii. And through the morning of July 1st, as the planet turned, the volley walked across the map. Minor blackouts over Bangladesh at 6:27 Universal Time, over northeast India, 16 minutes later, over Pakistan's southern coast, over the Gulf of Oman, then over Egypt just after 10. In less than a day, the sun had stamped its signature on the airwaves of half the planet. Somewhere under each of those footprints, someone keyed a radio and got static. That was the fast weapon. The slow one is still in transit. Several of the eruptions launched coronal mass ejections, clouds of magnetized plasma, 1 billion tons or more apiece, that take 1 to 3 days to cross the distance. The National Oceanic and Atmospheric Administration says at least one cloud from July 1st appears to have an Earth-directed component, with more still being analyzed. Its forecast calls for moderate geomagnetic storming, a G2 on the 5-step scale, as the holiday weekend begins, and minor storming through July 3rd. The headlines translated that into fireworks, auroras, possibly as far south as New York and Idaho. The Northern Lights are the postcard version of this story. The barrage that produced them is the story. To understand a machine gun, look at the gun. Right now, there are 5 numbered regions on the Earth-facing sun. 3 of them are trouble. A sunspot is a dark patch on the face of the sun where concentrated magnetic field punches through the surface. Cluster enough of them together and scientists number the area as an active region, the loaded chambers of the machine gun. Right now, the Earth-facing side of the sun carries 5 numbered regions. 3 of them hold what forecasters call notable magnetic complexity. Region 4479 is the one that fired the X1.1 and most of this week's volley. Its magnetic classification is beta gamma delta, and that label is the part worth understanding. A delta configuration means patches of opposite magnetic polarity are packed tightly together inside the same spot group. A tense, tangled arrangement. It is precisely the setup most capable of producing major flares because oppositely directed fields pressed hard against each other are fields primed to snap. Region 4478 carries the same beta gamma delta classification. It is the largest region on the disk. It is kept growing, and it is rotating toward the center of the sun's face, the position where anything it fires is aimed at Earth. Region 4480, its neighbor, is younger and developing fast. One more number tells you how loud the sun is right now. The 10.7 centimeter radio flux, a standard measure of overall solar activity, is sitting around 201, a level you normally only see around the peak years of a solar cycle. Complexity explains what a region can do. It does not explain why one region does it 10 times in a day. How does one patch of the sun fire 10 times in a day? The answer starts with what a flare does not do. A flare releases a burst of the magnetic energy stored above an active region, but it does not dismantle the region itself. The dark spots remain, the twisted field remains. And from below, the sun keeps feeding the structure. Fresh magnetic field rises through the surface, and the churning motion of the solar plasma shears and winds it tighter. In effect, the chamber reloads. A large flare can release more energy than millions of nuclear weapons combined and leave the arsenal that produced it standing. Scientists even have a name for the result: homologous flares, near identical eruptions firing again and again from the same magnetic architecture, sometimes hours apart, sometimes minutes. A delta region is built for exactly this. Those tightly packed patches of opposite polarity do not release their tension in one clean break. They snap, reconnect, load again, and snap again, for as long as the collision of fields underneath keeps pumping energy into the system. That is what region 4479 spent 24 hours doing. Same structure, same trigger, different bullet each time. And if that sounds extraordinary, here is the uncomfortable part. It was not even the most extreme performance of the year. Rewind to the first days of February. A region designated 4366 had just emerged and grown at startling speed in barely a few days. Within a single 24-hour stretch, it fired roughly 18 M-class flares and 3 X-class flares, including an X 8.3, which still stands as the strongest flare of 2026. At its peak, it managed 5 X-class flares in just 2 days. Over its lifetime, Forecast Center records credit that one region with dozens of M-class events and 6 X-class blasts, and observers called it the most active sunspot of the entire solar cycle. So this week's barrage is not a freak occurrence. It is the second machine gun episode in 5 months. The sun has developed a habit. Now hold that habit against the forecasts. On the day before the X1.1, the official probability of an X-class flare stood at roughly 10%. 10% is not a warning. 10% is background noise. The eruption fired anyway, followed by 10 more in the M-class. And as the plasma clouds from those blasts stacked up on their way to Earth, one of the field's most widely followed solar physicists put the situation in writing. The NOAA and NASA model predictions do not show all of the storms yet. The reason, she explained, is the pace itself, eruptions coming in such rapid succession that the models struggle to keep them separated. Sit with that sentence. The models do not show all the storms yet. It was written while those storms were already on their way, and it deserves a full look. Now, line up the numbers. On the morning of July 1st, hours after the X1.1 had already fired, the official daily forecast from the Space Weather Centers put the chance of M-class flares at 60% and the chance of another X-class event at just 10%. The sun answered with 10 M-class flares before the day was out. Only then, on July 2nd, did the numbers move, 70% and 20%. Read that sequence again. The forecast did not lead the sun. The forecast followed it, a day behind, adjusting to eruptions that had already happened. The same lag shows up in the storm traffic. The solar physicist tracking the barrage counted more than 5 separate solar storms on their way to Earth, at least 3 of them with good chances of lighting up the sky with auroras. The first, by her estimate, could arrive before 8 in the morning, Eastern Time, on July 3rd. The official agencies, at the same moment, could confirm less. At least one cloud from July 1st appears to have an Earth-directed component, with further analysis still underway, and the rest of the barrage's ejections still being analyzed. While less than a day out. There is an honest physical reason the models fall behind. When eruptions launch hours apart, their plasma clouds do not travel in single file. Faster ones plow into slower ones. They merge, distort, and cannibalize each other in transit, so that what arrives at Earth may be one storm, or 3, or something in between. And the property that decides a storm's real strength, the orientation of the magnetic field inside the cloud, cannot be measured at all until the cloud sweeps past a monitoring satellite roughly 1.5 million kilometers upstream of Earth. At solar wind speeds, that is under an hour of warning, sometimes closer to 15 minutes. For a stack of overlapping clouds, the models are, in effect, forecasting a pileup in the dark, so the eruptions outran the probabilities. The storm count outran the tracking, and the final answer on strength will arrive less than an hour before the storms do. Which raises the question this whole week has been building toward: is space weather forecasting broken? Let us take that question seriously, and then let us look at what the record actually shows. Here is the most honest version of that claim, the version a careful scientist would actually defend. Predicting exactly when a solar flare will fire is an unsolved problem. Not underfunded, not half-finished. Unsolved. What the forecast centers issue every day are probabilities, a percentage chance that a region of a given size and complexity will produce a flare of a given class within 24 hours. There is no operational model on Earth that can say region 4479 will erupt at 2050 Universal Time. A recent review of the flare forecasting platforms in actual use reached the same conclusion in drier language. Their real-world performance carries documented limitations that everyone in the field acknowledges. How unsolved is it? Consider what it took to catch a flare in the act of being born. Because an active region had been firing for days, several observatories were already pointed at it. Among them, a NASA spacecraft called IRIS, built to study a thin slice of the solar atmosphere in extreme detail. By pure luck of scheduling, IRIS recorded nearly 5 uninterrupted hours of the region before it unleashed an X9, one of the most powerful flares of this entire solar cycle. When researchers dug into the data this year, they found that the plasma's brightness, motion, and turbulence had all begun rising roughly 3 hours before the eruption, and that the region was pulsing in slow, regular cycles, one repeating every 7 to 10 minutes, another every 18 to 21 minutes, concentrated along the exact boundary where opposite magnetic fields press together. The lead researcher's reaction says everything about where this science stands. He was not expecting what he found. Warning signs before big flares may genuinely exist, but we are only now learning to read them, and only when a spacecraft happens to be staring at the right patch of sun at the right time. 3 hours of possible warning, visible only in hindsight. So, is the forecasting broken? Hold it to the standard of what it claims to be. A 10% forecast is not a promise of quiet. It is a statement that, on roughly 1 day in 10 like this one, the flare fires. If 10% days never produced X-class flares, the number itself would be wrong. Across the full catalog of forecasts, the percentages are tested against outcomes, and they hold up as probabilities. What they were never designed to be is a schedule. Judged as probabilities, this week's numbers did not fail. Judged as a schedule, they were never going to succeed, because no such schedule exists. Now hold the system to the standard of what it actually protects. The flare radiation itself arrives with the light about 8 minutes from Sun to Earth. The same instant detection becomes possible. No warning system in physics can beat that. What the system can do is grade the hit and route the alert, and it did. Every blackout this week was measured, classified between R1 and R3, and passed without exceeding what the affected industries are built to absorb. And on the slower threat, the coronal mass ejections, the machinery worked with room to spare. Storm watches for the weekend went out while the clouds were still more than a day away. The honest verdict, then, cuts both ways. Scientists were not ready, in the precise sense that the sun's timing and its rapid-fire succession still outrun every model built to anticipate them, and scientists were entirely ready, in the sense that the warning system caught, graded, and communicated every blow within its design. The gap is real, the failure is not. But the truly uncomfortable part is not this week's gap at all. It is that the sun has been running ahead of the forecasts for 6 straight years. December 2019, an international panel convened by NOAA, NASA, and the world's space weather services publishes its official forecast for the solar cycle that is just beginning. The panel has weighed nearly 50 competing predictions from the scientific community, and its consensus is calm. A weak cycle peaking around July of 2025, with a maximum sunspot number of about 115, roughly a repeat of the weakest cycle in a century. The sun ignored that forecast almost immediately. Activity ran above the predicted curve from the cycle's first years. By late 2023, the situation had grown awkward enough that the American Forecast Center did something rare. It revised the prediction mid-cycle, moving the peak a full year earlier and raising the ceiling to between 137 and 173, a shift its own solar cycle lead publicly called a significant change. The final scorecard settled the argument. The cycle's smoothed maximum arrived in October 2024 at about 161. The sun had beaten the original official forecast by roughly 40%. And here is where the story should have quieted down. A solar cycle declines after its peak, and this one is declining on schedule. 2026 has already logged the first blank, spotless days on the sun in 4 years. But look at what the decline has actually delivered. The strongest geomagnetic storm in more than 2 decades, in May 2024, major storms in November 2025, and again in January 2026. February's rapid-fire region with its X 8.3, the strongest flare of the year. And now this week's barrage. 10 M-class flares in a day, in a year, the original forecast expected to be sliding toward quiet. That pattern is not an anomaly. It is the pattern. The Halloween storms of 2003, among the most violent space weather ever recorded, struck 2 full years after that cycle's maximum. The great storms of September 2017 came 3.5 years after that cycle's peak. The declining phase of a solar cycle does not fade politely. It throws haymakers on the way down. A quieter sun, in other words, is not a safer sun. Which brings us back to the disk of the sun as it looks right now, and to the region that is turning to face us. So, where does this leave us? In the immediate term, watching the sky. The first of the storm clouds could reach Earth before 8 in the morning, Eastern Time on July 3rd, with plasma from the June 30th X-class flare leading the way. The official forecast calls for moderate G2 storming in the overnight window and minor storming through the day that follows. To be clear about scale, a G2 is a moderate storm, the kind that pushes auroras farther south and gives grid operators a busy shift, not a crisis. How strong it actually gets depends on 2 things no one can measure yet: how those stacked clouds have merged and mangled each other in transit, and which way the magnetic field inside them points when it finally sweeps past the monitoring satellites. An answer that arrives, as always, less than an hour ahead of the storm itself. Several of the barrage's ejections are still being analyzed. The forecast can move in either direction, and the forecasters say so openly. That candor is not a weakness. It is the most accurate sentence in the whole forecast. The second thing to watch is slower, and it matters more. Region 4478, the largest active region on the disk, still carrying that tense beta-gamma-delta configuration, still growing, is rotating steadily toward the center of the sun's face. It is the same region forecasters flagged when it first turned into view about a week ago. Back then, it sat near the edge, its energy pointed away from us. That has changed. Geometry is destiny in space weather. A complex region parked at disk center is a region whose flares strike the daylight side of Earth at full force, and whose ejections, if it launches them, are aimed straight down the corridor toward us. Over the coming days, 4478 will occupy exactly that position. None of what that could mean is speculative. A stronger flare from a disk center region produces wider and deeper radio blackouts within minutes of the flash. An Earth-directed ejection from the same position drives a stronger geomagnetic storm from 1 to 3 days later, the kind of event that stresses power grids, complicates satellite operations, and degrades navigation and communication signals. These are the documented, well-understood consequences of a flare-capable region pointed directly at a planet. They are also, for now, only possibilities. The region may fade. Complex regions sometimes do, but betting on that has not been a winning strategy in 2026. The honest verdict on this week, then, is narrower and stranger than the headline. The sun did not break its rules. 10 flares in a day is the sun being the sun, a star in the loud, unpredictable descent from its peak. What this week exposed is the distance between watching and predicting. We saw every eruption the moment it happened. We could not see a single one coming. Scientists weren't ready, not because anyone failed, but because the sun is still faster than its forecasts in the exact phase of the cycle when history says to expect the haymaker. So keep your eye on the storm arrivals through the holiday weekend and temper the Aurora hopes with one practical note. Short summer nights leave only a narrow window of real darkness to see them. Watch region 4478 as it crosses the center of the disk in the coming days. And remember what the numbers in this story kept saying. From the 10% that fired to the forecast that was rewritten mid-cycle, the sun is under no obligation to match our models. We will be tracking all of it as it develops.